Hello everyone. We're continuing to work on solving inequalities. And for this video, we're going to solve one exponential inequality. And the other one, we're going to solve a log inequality. And in particular, for that log inequality, we need to worry about domain issues. And that is because if you try to do in your calculator the log of 0, it's going to give you an error. If you try to do a log of a negative number, it's going to give you an error. And so we need to worry about that. And so as we've been doing, our first step is to take and we want to solve the corresponding equation, which just means that instead of writing an inequality, we're going to do an equals. And so for this problem here, we're going to add 6 to both sides. When we do that, we're going to divide by 3. And that's so we can get to this point where what we've done is we've isolated the E. And the reason that we want to isolate this E is because we want to get it so that we can do, well, we want to undo the E, and what undoes the E is the natural log. And so you can see at this next step, I did the natural log on both sides. I canceled out the natural log and the E, and just left with 2x minus 1. From here, add 1 to both sides. From there, divide both sides by 2. And we end up getting our solution here, which is the natural log of 5 plus 1 divided by 2. And if I write this as a decimal, it's going to be 1.3047. It just goes on, and it would go on forever if I had a calculator that allowed it to do that. We don't need that level of accuracy for what we're doing. Letting x be equal to 1.3 is going to be fine. And I want to remind everybody, what does this 1.3 mean? Well, if I were to plug that 1.3 back into the equation, so if I were to do 3e to the 2 times, and 1.3 wouldn't be enough. We'd have to do 1.3047. We'd have to do all those numbers, and then minus 1, minus 6, greater than or equal to 9, and what we would get out of it is 9 is greater than or equal to 9. And so what I found out of this is the point of equilibrium. So this is where both sides are equal to each other, and what we're interested in doing is either shading into the right of that or shading into the left of that. So we'll take that 1.3 and we'll move on to the next step. Okay, so the next step. What we need to do is we need to consider any domain issues. And for exponentials, there are no domain issues. And so we don't have to consider anything for this. So for exponentials, no domain issues. And so what this means is that if I had to take any x value and I plug it into that formula in my calculator, it will always give a number back. And so what I do is I set up this 1.3. This is the point of equilibrium right here. And I know that on one side or the other, I'm going to shade it in. So I'm going to pick a value from each side at test point. I picked x is equal to 0. When I plug that in, I end up getting this negative 4.89 greater than or equal to 9. That's false. And so I don't shade. Um, it's probably going to be the case that the other side will shade, but I need to check anyway. So I picked 2 as my value. When I plug that in, I get 54.39 greater than or equal to 9. That is true, and so I shaded this side. And so with that, we move into step 3. One is the number line. Well, I did the number line. That is above already. So you want to be proficient in all 3 of these. The interval notation. So what I see here is that it goes from 1.3 and then it shades this way, and it will continue on forever. I also noticed that because it was a greater than or equal to in the original problem, that means that this is going to be a filled-in circle. So interval notation begins with a bracket, 1.3, and it goes out to infinity. Anytime we do infinity, we use parentheses. For inequality notation, when we're talking about going to the right, this is going to be x is greater than, in this case, greater than or equal to 1.3. And so here we have greater than always means to the right. So I'll erase this and then we'll go on and we'll do the log equation. Same process, except for that the log equation, we are going to have a domain issue that we'll need to consider. Okay, so here's the log equation that we have. It's going to be the log of 3x plus 2 is going to be less than 2. And remember that I'm sure a lot of you do, that if there's nothing written there, that means a log base 10. We'll start out the same way we've been starting on all these, and that will turn it into an equal sign. In this particular case, solving a log equation, many of you do this where you do the snail method. So 10 squared is equal to 3x plus 2. We get our equation here. It's linear, so we'll go about solving it. And when we solve it, we get 98 over 3, which as a decimal is 32, with the 0.666 repeating. I just rounded that to 32.7. Again, we don't have to be accurate with it in terms of our calculations. We just need to get some idea on where this lives. And so the second step is going to be consider the domain issues and create the number line to test points. The domain issues in this case, you cannot have the log of 0. It will give you an error. You cannot do the log of negative. That will give you an error as well. So what we have to consider is where the inside, so this is the inside of the log, we have to consider where the inside is positive. We require that it's going to be bigger than 0. Well, if I take that language bigger than 0, then that means that I can take 3x plus 2 and I can make it bigger than 0. And if I solve this, I'm going to get minus 2 on both sides. I get 3x is greater than negative 2. Divide both sides by 3. And this is going to give me x is greater than or equal to negative 2/3. Excuse me, let me fix this. Strictly greater than negative 2/3. So what this means is that the x values have to be greater than negative 2/3. If it's equal to 2/3, that's a problem because that means we're going to get an error in our calculator. If it's the case where it's less than 2/3, let's say that x was negative 10, which is less than 2/3, that's a problem because we're going to get an error in our calculator. And so thinking about how we're going to actually use this, we'll actually take one of the areas of the number line, and we don't have to do any test points. That doesn't mean that you can't do test points, but you don't have to do test points on it. And so what I mean is this. So I've created the number line here. And if you notice, what I've got here is that this is the area where x is less than or equal to 2/3. I can't do it there. I would get an error. Let's say that I didn't realize that. And let's just say that I wanted to let x be equal to negative 10. Well, then I would get the log of 3 times negative 10 plus 2 is going to be less than 2. And what I would get if I did this in my calculator, I would get an error. So it's not terrible. If you don't realize that you don't need to test point, you can test the point and you'll figure it out. So one thing that I do need to do, I do need to have an open circle because it is a less than, not a less than or equal to, at 32.7. I also have to include this negative 2/3 as well. And so with that, I do my technique. I pick an X value, I plug it in. If I get a true value, I shade it. In this case, I shade it. Over here, I picked 40 when I plug that in, and I calculated I get a false value. That means no shading. And so then I've got it. So the number line, this is done. That's above. In this case, when I have, for the interval notation, I have between two values. And so what I'm going to do basically is I'm going to take and I'm just going to put X in between these two, and I'm going to get negative 2/3 is less than X is less than 32.7. Excuse me, this is the inequality notation here. This belongs here. This is the inequality notation. For the interval notation, it is going to be between negative 2/3 and 32.7. Okay, so that's it. We'll get lots more problems to work on. We'll continue working on the domain. It is an issue that we think about the entire semester. We'll just continue improving upon it. So thanks, and we'll see you soon.